We're now going to look at a more enriched bargaining game where there are two periods. So the one receiving the offer, rather than simply rejecting it, could make a counteroffer. So in period 1, player 1 makes an offer to player 2. Player 2 can either accept or reject. If player 2 accepts, then the offer made by player 1 determines their payoffs. If player 2 rejects, then player 2 gets to make an offer. So that's the counteroffer. And if player 1 accepts, the game ends and they get payoffs determined by player 2's offer. Otherwise, player 1 rejects and they both get 0. However, we're going to assume here that the players are both impatient, so they have some discount factors, according to which they discount the payoff from the second period. The reason players discount future payoffs is because there's a lag between the first and the second period. So suppose there's some time that passes between the first and the second period. Then receiving a payoff tomorrow or in a week, or perhaps in a year, however long the period is not as good as receiving a payoff today. So receiving $1 tomorrow is not as good as receiving $1 today. Indeed, receiving $1 tomorrow is going to be worth less than $1 today. So player 1 in the first period makes this offer of M1 to player 2. Player 2 can either accept it or reject it. If he accepts it, the game ends and the payoffs are going to be determined by M1. So player 1 gets to keep 1 minus M1 and player 2 receives whatever player 1 had offered. If player 2 rejects the offer, then the game continues to the next period. Should the game proceed to the second period, then it's player 2's turn to make an offer. Player 2 offers M2 to player 1. Player 1 can either accept or reject that offer. If she accepts the offer, then the payoffs are determined by M2. Player 1 gets M2, but because she's impatient and her patience is determined by her discount factor, she gets M2, but receiving M2 in the second round is only worth delta 1, her discount factor, times M2. And player 2 gets the remainder of the surplus, which is 1 minus M2, but it's only worth delta 2 times 1 minus M2. If player 1 were to reject player 2's offer, then the payoffs are just 0 for both players. And in either case, the game ends. Let's now draw the extensive form of this game. So we have here the initial node, where player 1 makes an offer of M1 to player 2. Player 2 can then either accept or reject that offer. If player 2 accepts, player 2 gets M1, player 1 keeps the rest. If player 2 rejects, then player 2 gets to make an offer of M2 to player 1. Player 1 can then accept or reject. If she accepts it, player 1 gets M2, but discounts that by delta 1. Remember, delta 1 is some number between 0 and 1. And player 2 keeps the rest of 1 minus M2 and discounts that by delta 2. Again, delta 2 is some number between 0 and 1. If player 1 rejects M2, they both get a payoff of 0. It's important to note here that these discount factors are representing the patience of the players. Just so we understand what's going on here, think of the extremes here. Think of 0 and 1. Let's look at what it means for a player to have a discount factor of 1. It means that this player is perfectly substituting payoff tomorrow and payoff today. So whether you pay me tomorrow or you pay me today, it doesn't make a difference to me. I'm perfectly patient. Tomorrow is as good as today. If I have a discount factor of 0, on the other hand, tomorrow is completely useless to me. I only care about today. So if delta 1, for example, were 0, then proceeding to the second round would give player 1 a payoff of 0. So the higher delta is, the more patient the player is. Now let's try and figure out what the subgame perfect equilibria are for this two-stage game. The first thing we want to note here is what happens in the subgame. So let's have a look at the subgame starting in period 2. If we look at this part of this game tree, this is very familiar to us. That's exactly the ultimatum game. And we've already solved that. We know exactly what the equilibrium of that is. There's a unique equilibrium here, and it's for player 2 to choose M2 equals 0. The only difference here is that we've multiplied the payoffs by the discount factor, but that doesn't change the reasoning that brought us to the conclusion that the equilibrium is for player 2 to propose M2 equals 0. So then we know how the second period should be solved, and we know from the analysis of the ultimatum game that player 2 would offer M2 equals 0. Since the unique equilibrium of this subgame is for player 2 to make an offer of 0 and for player 1 to accept any offer, the payoffs from this subgame are necessarily going to be 0 and delta 2. So what we can do is to quote-unquote prune the tree and replace that subgame with those payoffs and then resolve for the equilibrium of what remains. So let's do that. Let's draw the pruned tree, where we've replaced the subgame starting in the second period with these payoffs 0 and delta 2. So once we've replaced the subgame, starting with the rejection by player 2, so starting in the second period, with the payoffs that they would get in that subgame, and so we call this a pruning of this tree. So once we've pruned this tree accordingly, we end up with a game tree that looks like this. Player 1 makes an offer of M1, player 2 can either accept or reject that offer. If player 2 accepts the offer, then they get the payoffs of 1 minus M1 and M1 respectively. And if player 2 rejects that offer, they get a payoffs of 0 and delta 2 respectively. So we can repeat our analysis very similarly to the ultimatum game to figure out what the equilibria of this game are. Look at this subgame. What should player 2 do? So in the subgame, where player 1 has offered M1 to player 2, if M1 is bigger than delta 2, remember player 2 is comparing accept and reject. If he accepts, he gets M1. If he rejects, he gets delta 2. So if M1 is bigger than delta 2, he should obviously accept. On the other hand, if M1 is less than delta 2, then reject is a better option than accept, because delta 2 is higher than M1. Finally, if they're equal, then player 2 is indifferent between A and R. So both A and R are optimal. So for any strategy that player 2 plays in an equilibrium, player 2 must always accept anything higher than delta 2 and must always reject anything lower than delta 2. But when exactly delta 2 is offered, he could accept or reject. However, if he rejects, by the same reasoning that we had seen earlier for the ultimatum game, player 1 wouldn't have a best response. So that can't be an equilibrium either. So it has to be that when indifferent, player 2 accepts. So following the same exact reasoning that we did for the ultimatum game, we can conclude that the unique subgame perfect equilibrium is for player 1 to offer exactly delta 2, and for player 2 to accept any offer that's at least as high as delta 2. So what we see now then is that the unique subgame perfect equilibrium payoffs are 1 minus delta 2 and delta 2. In other words, the bargaining power of player 1 is 1 minus delta 2, and the bargaining power of player 2 is delta 2. So we see here that the patience of the players, in particular, because we have only 2 rounds, the patience of player 2 determines the bargaining power. Another really notable fact here is that because they're impatient, waiting till later rounds to reach an agreement would cause a loss of value because they discount whatever they end up getting. So the sum of their payoffs would always be lower than 1 in any period but the first period. So efficiency would dictate that the players agree on a division in the very first period. And indeed, we see that that's what happens here. Now, in general, even if there were not 2 periods, if we had an arbitrary number of periods, we had 3, 4, some arbitrary number t, we can still show using this very similar reasoning by backwards induction that the players would reach an agreement in the first period. Moreover, the bargaining powers would be, in other words, the shares of the division would be determined by their discount factors. In this particular case, because we only have 2 periods, it's only determined by player 2's discount factor, but it would also involve player 1's discount factor if there were more periods. You might wonder that it seems strange that this game theoretic model predicts that there would be no rejected offers, that everything would happen seamlessly and without delay, that the players would very efficiently reach an agreement in the very first round. But it's important to note that this game is a game of perfect information. In reality, many negotiating circumstances are not games of perfect information. So when there isn't perfect information, when, for example, if player 1 doesn't know what delta 2 is, then player 1 wouldn't be able to offer exactly delta 2. And that could lead to delays or breakdowns in negotiation. And we'll see some of these issues later on in the course.